Then, with the delta, I mean, the symbol I want like that is the usual B, because the other one is 0. Maybe that becomes something. Now, I decided I tried whatever this was because the way Keller does things, he just resolved a big formula which he's going to show in a minute. And I wanted to avoid that. I wanted to go to the structure of the manifold, to how it relates to the metric, which is the only thing I assumed about the manifold. This challenge
I think the margins are big enough, you can also make it a little bigger.
Not bad. Keller introduced this differentiation, and as you see, here there are many terms. He's using quantities with indices. So this is for one series of indices, this is for another series, and this is for another series. I found it horrible. But since I know Cartan, I will know what is behind this. This is for valueless, and this is for valueless. This is for the differential forms. We can remove this, but still, one modulus, where does this come from? There can be a logic to it, and
close
the water.
Door and window.
Okay, so I try to avoid this by going to, okay, the metric. Going to the metric and nothing else, and see what one canonically can get from that. And I avoid all that, because who's going to, I don't know why people do not use Keller, maybe because there are many difficulties like this. So mine is very far from being perfect, but I hope that people should be disciples of you, okay? One day we may know this more the way you like it. I have gone a little bit in that direction because Cartan is less prone to using coordinates than Keller is. Okay, thank you. That's what I wanted to say. Okay.
So this is going to fine. The basic calculus is a separate file, it's a presentation of this year, not of last year. And so I will explain the most important things. Anyway, we here have all the first, I want to make to show an example of a circle. We have Riemann. This is a graph of Riemann, which was about the geometry derivatives. Translated by Clifford, by William Clifford. Okay, so we have Clifford. Then we have Cartan. Cartan over the word of Rim. Cartan. In the introduction of the book, the System of Transylvania. Riemann, Clifford, Cartan. And Cartan is speaking about Keller. It's Keller. It has been generalized and by several specialists, Eric Keller, who has studied intuitive systems. The notation of the differential form, this notation is of Eric Keller to Cartan. And so Keller finally made three. This way. Riemann, Cartan, so we close the set. Okay? All is related and all methods are related. Well, why this part about affine coordinate? Because there is a question I believe has importance, which is the relation between the geometric directions of the differentials and of vectors. Let us consider the origin and a point in the coordinate system. We can write coordinates in this way. These are the vectors of the basis. Let us make a linear transformation of these vectors to find other vectors. We can write this matrix. We can make the inversion of this change, and then we here have the entries of the matrix. So if we take this equality and put this other equality, we have this expression, and from here we deduce how the coordinates are transformed under this transformation. The coordinates are transformed with the entries of the inverse matrix, not with the matrix or the transformation of the vectors. So if we take differences of coordinates, the transformation is the same. And from here to pass to differential is a small pass, but this transformation is the same. So differentials of the coordinates are transformed according to the entries of the inverse matrix or the transformation of the vectors of the basis. This means that they are transformed in the same way as the vectors of the dual basis. Okay? Differentials are transformed as the vector of the dual basis. We can check this. Okay? The dual basis now are bases of vectors in which each vector multiplied by the other vectors of the basis are 0, except for which is 0. In the 3 dimensions, this means take the plane of 2 vectors and to take the perpendicular dimension. This is the concept of dual basis we have. The dual basis is usually used just in crystallography. The directions of the crystallographic planes are dual of the directions of the vectors of the network, of the crystallographic. It is not in mathematics because we only need one basis to any and one basis. We do not need 2 bases. But what I am showing here is that differentials are transformed as the vectors of the dual basis. Some usual confusion is to think that differentials are transformed as the vectors of the basis. This is not right. The differentials coordinates are transformed as the vectors of the dual basis. If the basis is orthogonal, then the transformations is almost the same, but not the same, because we can have the same. Okay? Well, after this appraisal, if we have a basis, of course, differentials allows us to pass from affine geometry to differential geometry to binary coordinates and so on, because differential is locally static. Okay? So we can have in general any basis, given as these scalar products. This is just the tensor. Okay? The dual basis can be from the original basis in this way. Of course, the metric tensor must be symmetric and must have determinant different from zero in order to not collapse the system of coordinates. Okay? A geometric vision, an example of what I am speaking in the plane. We have here the line coordinates, okay? But the differential, the direction of differential is perpendicular to the line coordinates. In general speaking, for any dimension, the differential of a coordinate is perpendicular to the orthogonal to the hyperplanes with the equation coordinate equal to constant. These are hyperplanes, and then we see or can say that the differential of the coordinate is just perpendicular to this place. However, the line coordinates, not the plane coordinates, the line coordinates in general on the frame of coordinates have other directions, not coinciding with the direction of the differentials, but they are related by one. Okay? Well, we will see an example later in the space-time. In the space-time. Sorry. Well, Keller, Jose has introduced Keller before. Keller was considered was the scalar product of differential forms. He wrote, which is the same as a symmetric uniform product, but this is the same. Okay? To write this. Equal to, in general, to the metric tensor, two times the metric tensor.
Subscripts.
What?
All subscripts or all superscripts?
Yes, of course. Okay? Or subscripts or subscripts. We use subscripts for the vectors and subscripts for the differentials of the coordinates. Then, because the differential calculus you have studied at the faculties do not include this. Okay? This is a new issue. And it is similar, it is mimetic of the scalar product of the vector of the basis. If the basis is not orthogonal, you also have I sub I, scalar A sub rho equal to the metric tensor but with subscript. Because of this, instead of the transaction. Okay, then this allows to define the norm of a differential form. We have a differential form, we apply this, and the result is this. Okay? Of course, we must take the absolute value if we want a positive norm or so on. But this is the result. It is the same as the similar, not the same, the similar as the norm of a vector in a vector space. It works almost in the same way. Okay? For a vector, the norm is found in this way. These components are obtained. These components by multiplication and contraction with the metric tensor. In this way. Okay? This is the relation between components, vectorial components in a vector basis, and components of a differential form. The relation is to pass from one to the other, from one to the other. So the easier example is the Cartesian coordinates. Okay? We have a basis, the squares of all differentials of the Cartesian coordinates in the Euclidean space, not only Cartesian but in the Euclidean space, are equal to +1. And then, of course, a differential form in this way is has just this one. This is absolutely consistent in differentiation of coordinates and so on, function and so on. The algebraic consistency is perfect. There is no. Yes, tell me. Tell me.
You wrote, after 22, you wrote GIA is the identity.
What?
After 22,
to line 2,
after.
One. Yes, the unit.
Next slide.
Next sentence.
Next line.
No.
on the left, G.
This is the identity.
The identity matrix.
How could be metric identity? I don't understand.
No,
identity.
matrix.
Matrix identity.
Yes, it is.
Unit matrix. It is unit
Yes.
matrix.
For Euclidean coordinates. Speaking for Euclidean coordinates. This. We are in the Euclidean case.
But such matrix has square of this matrix is still the same identity. But metric tensor has no square.
Then how you prefer to name the identity tensor?
You should not, I think that metric should never be presented as a matrix, never.
Yeah.
Because columns and rows are totally different. It's not endomorphism. It's not mapping column to column. It's mapping column to rows.
Yeah.
So you cannot present as a matrix.
But we have in the rows we have or components of vectors of components of a different form. And in the rows also.
But the basis in vectors, basis in covectors, they are independent.
But one question, one question for you. The difference between vectors and covectors, or there is a difference, a conceptual difference between vectors and covectors, or are simply the components which change, because we are using one basis or one basis. There is difference in the nature or only the components?
Vector is independent on components, and covector is independent on covectors.
And which is the difference between vector and covectors?
No, they are different, like men different from a woman. They are different.
Well, not in these times.
Except for the question of taking rows and columns, but
they are dual to each other, but they are different.
Okay, there is a school of thought, which is the Hestenes school of thought.
No. Hestenes is presenting always metric as a matrix.
No, wait a minute.
But here we are doing a scalar process of differential forms, and with the metrics. We can do this scalar process. But the differential form on the left and on the right have the same nature. We are not multiplying one kind of differential forms with another kind of differential forms. They have the same nature. Well, I will tell you we can. If we make a rotation, then we see that the norm is preserved. We can do these differentials, not only in vectors, but differentials. You usually make rotations with vectors, but we can rotate differentials. And the result is just similar. Not exactly the same, but almost similar. Okay? So the vectorial behavior of differential is obvious. Okay? For me, a differential is not a scalar quantity. It is an entity that has a geometric direction in the space of directions, in the kind of space of time and so on, but they have directions. Okay? And with Keller, they have analysis norm. It is not usual in the differential calculus. The external differential calculus cannot have norm. Cannot have norm because the exterior product do not have norm. So it is impossible that calculus of exterior differentials, exterior differentiation, it's not possible. Okay? So we see that the one is preserved. The same for my vector, we can make the rotations, make the substitutions, and see that the one is preserved. They are just results of which are similar with vectors. Okay? We make substitutions and make some. This is an example for triangle. Okay? And we see that the norm is preserved. The norm is preserved also for my vector. This is a drawing of what can we understand or what can be mean about differentials. This is the elemental element of bond, okay? And the edge of this element of bond are just the differentials, not of the coordinates, because this is of a spherical coordinates. In Cartesian coordinates will be differential of x, of y, and z. But in spherical coordinates, and this is just the change from Cartesian coordinates to any kind of coordinates, there are these factors which are just that coming from the vectors. Okay. Yes.
You are making all these calculus on click or algebra.
Yes, of course. Okay. Because I have a scalar product of differentials, so I am doing now scalar Clifford algebra of differentials. Scalar means Clifford.
This is what I call dx squared.
I read something about like a little bit of the same notation, but from vectoral spaces to vectoral spaces, and making all these calculus structure, all the differentiation, you know, and differentiation. So I'm trying to understand what do you mean when you are working with Clifford algebra?
Yes, we but anyway, the important point is that the usual working with a mixing of vectors and differentials of coordinates is not necessary at all, because the differentials themselves are enough to describe all the vectorial structure of all these forms. Okay? Only needs the scalar product of differential forms. Is the new thing. The new thing with respect to study and faculties. Okay? But perhaps in 10 years or in 20 years, every student will start doing this. It depends on the curriculum of the universities. Okay? So let us go. Let us see the consistency of this scalar product of differentials. We have here the spherical coordinates. We can differentiate in the usual way. Okay? So this is a scalar numerator. No. This is a numerator of vectorial kind, because we have a linear combination of differentials. These differentials are pointing in different directions. Right? And this is the resulting differential as a linear combination, as a vector composed by vectorial addition of these differentials with these coefficients. Okay, let us go to differential of theta and of phi. We can see many things. For instance, which is the norm of differential of we apply our theory and we see that the norm is 1. Okay? Differential of theta, which is its norm. We can also apply the Pythagorean theorem, because these differentials are orthogonal, and we find this norm. Which is the differential of the same. We find here the norms of the differentials of these coordinates, which are not one in general, because they are linear coordinates. They are not coordinates. Okay? They are just the coefficients of an orthogonal method, because they are orthogonal coordinates. Just these coefficients, 1, and L by sine of z. These are just the norms, the integers of the norms of the differentials. Cardan wrote a differential of a point as a linear combination of the omegas. Therefore, the omegas are just the differential forms having unity norm. Okay? Just this, if the norm of S sub D is the unity, then the norm of omega sub D is the unity. Okay? Omega sub D for orthogonal coordinates are just this, which is what we are finding here. This is 1 divided by the scale factor of theta, which is R, and the scale factor of phi, which is by sine. Okay? So this is very important because we have two options, or to work with omegas, which have a unity norm, or to work with the differential of the coordinates, which do not have unity norm. Well, for instance, how we can calculate the norm of a differential form given in spherical coordinates? The first thing is to write in the form including the scale factors. Then we x are called the scale factors. The physical components of differential form are the components of a differential form, but written in the basis of omegas, okay? Not in the basis of differential coordinates. Okay? These are the physical components, which mean the components of the corresponding vector, but taking into account one. Okay? In this case, for a clear space, these physical components are coincident with the component of the corresponding vector, but only in this clear space. Okay? So, if we use the components of written in the basis of differential coordinates, the norm is this. But using the physical components, the norm is the basis of omega. This is in the basis of differential coordinates. Okay? This is the concept of norm in chemistry. Of course, we can go further and calculate the norm of a product of two differentials. Okay? This is a uniform product, but since the basis is orthogonal, is coincident with the exterior product. We can calculate this norm using this property of the norm of an element in a Clifford algebra, which is absolutely general, but really needs the assumption of something that I wrote in a paper last time. Okay? This is true, but not all the authors agree with this, but not because they have different opinion, simply because many times they are not able to define the norm of every element of the differential. But if one can define well the norm of every element of the differential, this is true. Just we can apply this and find the norm every to form is a form of weight, the equivalent of a kind, okay? And so on. Form. Okay? Well, let us go to this line. Now, at this moment, we have some discussion about notation. So, Vargas uses my notation, I am using another notation. But the important thing, yes, tell me.
Yes, Ramon. The D point U leads to confusion.
Yeah.
Okay, so Keller actually wrote D hot star U.
Yes, yes.
Okay, so because otherwise the problem that D point U has is that you take the components of D because D would be partial with respect to x1, dx1 plus partial and so on. And then you take the other one and you say, aha, I do the dot product. It doesn't work. It only works in Cartesian coordinates. So it is better not to use.
I agree with you, but this problem is the same problem that has the vector notation of vector analysis. The same problem.
Yeah, but you can avoid it.
The same problem.
Okay, you
It's
can
just the same
avoid it.
problem.
So what
If
you
we
say?
accept this notation, we must be able to accept this notation. Anyway, the notation of Keller is good to remind people that we must go through the Hodge dual. In this way. It's also a good notation. No, I am.
Well, he chose that notation. He doesn't go through the Hodge dual. When we use in the stereo calculus for the co-derivative, okay, that appears as a theorem, okay, not as a definition in the Keller calculus.
Okay, but exterior calculus, people uses the co-derivative, but exterior calculus just does not have them, because exterior calculus is degree 1, degree 2, degree 3, and so on. Not to the Venus. The Venus direction is just calculus. Okay? So, however, people have found something to the co-derivatives. It seems that this seems to work and so on, but this is not exterior calculus. Okay? No, I am also referring to this other notation. I am now writing in this way the Clifford differential. However, Jose is writing the partial symbol, the symbol of partial derivative for the Clifford differentiation.
Yeah, but most important is the notation for the last term.
Okay.
Okay, because that way, if you use it naively, you say, aha, D is this, U is that. You do the dot product and you get the wrong result. Whereas if you use dx mu contraction, Clifford contraction, with what I define, which is Keller, the covariant derivative, then that automatically takes into account the extra terms in the divergence when the coordinates are not Cartesian coordinates. Okay? So it looks very nice.
Yeah.
Yes. In equation 50,
Sure.
in 50 equation, you have letter D 3 times. 3 times D, D, D. You understand?
Yes.
In 50, in 50.
Equation 50.
Equation 50, 5, 0. You have
Yes.
symbol D 3 times.
Yes.
Every such symbol has totally different meaning. So 3 different concepts you denote by the same symbol. So this is homonomial. This is very confusing because every letter D has totally different meaning from another letter.
You are doing algebraically a different operation because one is an external operation and the other is a scalar operation. But the way of differentiation is the same. We only are taking directions and the operations with these directions. Okay? Because differentiation, I do not want to enter in the fundamentals of differentiation. But for me, if we have a point with a certain function. A function is a multiplicative case. We should go to take into account differential forms. And we have a surrounding. Then we must see how this differential form changes in this direction, in this direction. We will find terms of higher degree and other of lower degree. And this separation between the terms of higher degree and lower degree is but the geometric process of differentiation for me is the same. It's not different one from the other. Anyway, we can use the what notation we believe it is the better, it is the best. But it depends on the person, not everybody is thinking the same way.
If I may say, this happens many times because there is a conflict between symbolic representation and operational representation.
Yeah, but this is a problem of video.
Yeah,
Video, rotational, divergent is the different symbols.
But even for numbers, I mean, if you use by a symbolic approach, they mean something. If you use an operational level, they mean something else. But they are just the same.
But the geometric operation is the same. They are not different.
Yeah, that's the point. Our operational level.
Those are the importance.
Operational level for computation.
So there is no difference.
But you are getting yourself a problem with people like Svignew because, you parted ways there with Keller, because when Keller writes that, he used the Greek letter D on the left. Then that D in the first term and D star in the third term.
Okay.
So if you did that, fine. Or if you do as I do, which is that the symbol that looks like partial in the first term, the D in the second, and the Greek delta on the third.
Yeah, but my point is...
Three different symbols.
So you and I think similarly, okay? But you are having a problem with him, and I am not having that problem with him. Just because
No, this is important. This is important for just for disseminating knowledge, you know. I mean, the symbolic representation is fundamental to minimize ambiguities. Even if at the operational level, when you start counting, the operational is just the same, okay?
But
operational computation.
But anyway, this question has more or less been solved in vector analysis. This kind of expressions or expressions. We now that we use coordinate coordinates, we cannot just use what it seems to indicate. Okay? There are the corresponding operators that we must apply. This is the same in this case. Okay? The problem of implementation, but my point is, I think that the geometric operation is the same. Okay? So I do not use different symbols because we make a small translation from one point to the other to see how this differential form changes. Okay? Well,
it depends on different vector spaces.
sorry?
It depends on different vector spaces. You have plus in between.
So we are in geometric algebra. Geometric algebra includes spaces of different grades. Okay?
You will need the direct sum of many people.
Yeah. No. We will go through. Okay? Geometric algebra is any element of the geometric algebra can be a linear combination of exterior products of the vectors or the differential of the coordinates or the operators in between these operators. There is a grading and this also has
to use modern tools to blend this, say the odd degree red and the even degree symbols black, and it will be easier to read the formats.
That's it. You're saying colors.
Nowadays technology this is possible. Different terms, different degree.
yes,
Separated by color.
no, but initially, is graded. Okay? We have functions, vectors, vectors, and so on. Okay? But then in many problems, such as the quantum mechanics, there is a mixing of grades because the algebra allows the mixing of grades. Okay? They allow. Then the differentiation of the differential form, the Clifford differentiation, gives different grades.
So that would solve the problem. Let's see different D's. If you use color blending, you can see that.
Yeah, but my point is that really the geometric operation is the same because it's the variation of the differential form from one group to the other. There is only one geometric operation, but with different ways because we can take into account the collinear relation or the perpendicular relation. Okay, so we have different lines. Okay, but anyway, notation is now not common for everybody. Vargas differs from Keller, I differ from Vargas, and we will learn this more. Well, applications will have, for instance, in differential operations. In Cartesian coordinates, they are very easy. The applications 2 times of Clifford differential gives just the Laplacian. The square of the stereo differential, as you know, is 0. Okay? So that the only remaining term is this. And in Cartesian coordinates, we can apply these 0 rules of multiplication of differences. Anyway, for the general case, this works in Dracula also. We do not get this simple form for ordinary forms. The form is obtained through the rules of Keller. Okay? It's the same. We can, for a vector, to find the rotational, but also the divergence. If we go from grade 1 to grade 0, it is a scalar differentiation. Okay? The stereo differentiation gives the current, and the scalar differentiation gives the divergence. Yes?
There is any difference between applying a chain rule. There is any difference between chain rule in vectoral spaces and Clifford differential. Just like
Clifford differential.
Just like Clifford differential to a differential.
Yes.
And you leave the Laplacian.
Yes.
Okay. If I apply differential to the differential with the chain rule, what is the difference? Chain rule.
Chain rule.
Composition.
Chain rule. Composition.
Composition of differential form.
So what is the difference of like chain rule and Clifford differential? Because I think that gives the same.
Okay.
This is your topic, no? This the application.
Yeah.
No,
Well, the Keller differential, okay, is going to give you have 2 pieces. One I call D, the other one I call delta. You apply it twice. In principle, you are going to have 4 terms. Okay? dD, delta delta, d delta, and delta delta. dD is always going to be 0. Probably, if we are with the scalar value differential form, okay, it is going to be 0. Also, delta. Then you have 2 terms, d delta plus delta d. If you apply a function, okay, the delta of the scalar value differential form, 0 form, is 0. So it reduces to 1 term. So the Laplacian could have between 1 and 4 terms. It depends on, in principle it has 4 terms.
Here you got 10 terms, but maybe
What do you mean 10 terms?
3 terms.
No, less than 3. Which 3 are you talking?
No.
We are talking about
50.
yeah, Fórmula 56?
No, más
No, en la
54.
A 54.
54.
There.
54.
No, ahí hay solo.
This is 0. Because the
Ah,
square of
but
the
you
external
told me
distance.
that it was 0. Because with the chain rule, you
No,
have
okay,
it to
I'll do differentiation. Let him finish it at the end. I can answer those questions, which are not coming and coming.
Okay. So we can apply this to linear coordinates, at least in an easy way to orthogonal to linear coordinates. The matrix is diagonal, okay? So we can use on the basis of the differential of the coordinates or the orthogonal basis, which is the basis of coordinates. Okay? Then the physical components always are the components of a differential form. The physical components are those written as linear combinations. The omegas función de la cuarenta. Then you see omegas has not 1, so the differential of this coordinate has as not the inverse of the space omega. Then Keller defined and proved that the scalar differentiation is just the inverse of Hodge dual of the differential of the Hodge dual of the differential, which is just the co-derivative. Okay? Which is but as I said before, co-derivative is not a concept of experimental calculus. It's a concept of Keller. Okay? The result is more or less is this, but there is owing to the permutations of the basis vectors in pseudoscalar. Zeta is the pseudoscalar. Here we have the pseudoscalar is the multiplication of the omegas and is equal to the external multiplication of the original coordinates with the square root of the determinant. Although I believe that here we need an absolute value. In many well, so these permutations give a final these changes. Okay? Yes?
It's assumed positive definite metric because otherwise this sign factor would be different. If you have negative values, there's an additional -1 to the power of something more. It's already assumed Euclidean type. Yeah, you have plus the number of minuses in the power.
Yeah, I don't remember this.
I also don't remember. We accidentally derived this yesterday.
Well, we can check it. Perhaps this is the inverse. I the inverse of the answer. I do not remember. Okay? Anyway, with this operation, indicated in this way as Jose has said, it is what we can understand as the scalar differentiation. It is just the property. Okay? Well, then a differential form, for instance, written in the orthogonal basis, then has these physical components. These physical components gives us the gradient of a function. This is the expression general for orthogonal to linear coordinates. Okay? The same for one form. If we take the Clifford differential of the gradient, only we get the Laplacian. The external differential of the external differential is 0, and only remain to the scalar differentiation. So we make these operations, the dual and inverse of the Hodge dual, and finally we get theorem computation. This which is just the analysis. So Keller calculus are giving us the differential operators, the necessary differential operators, but for all kinds of coordinates. Here I am considering only orthogonal coordinates, but it may be extended, of course, some word or any word to the basis of the the same. If we take one differential form in a orthogonal basis, then we have this A1, A2, and A3 are physical components, which is equivalent to the physical components of vectors. Equivalent, not equal. Always remember this. The components between a vector and between differential forms are equivalent, related, but not just equal because there is the question of duality. Okay? And then we make the differentiation, we pass to the orthonormal basis, and we find the expression of the rotation. These are the components of the rotation. If we make the scalar differentiation of this one form, then you see the components of the rotation. The physical components, these are the physical components of the rotation. We make the scalar differentiation, Hodge dual, exterior differentiation of the Hodge dual, and then again the inverse of Hodge dual. We finally find the expression of directions. Yeah. Well, this may be applied to the only thing that I will not explain it, only I introduce are two things. Firstly, that we can apply to space-time also. But we must take into account that we have a -1 in the metric tensor. Okay? This means that if the vector with arrows is this, there is a change in the temporal component when we write the differential. Do you remember, Jose, when I wrote a plus in the vector potential plus the scalar potential, I used to be, this is wrong! This is a minus sign! I was why minus sign? The reason is the duality. The bases are not equal but are dual, so we must put a minus sign. Okay? We go. Did the same in the angular momentum. We must make the change of the sign of the differential time, and we can apply this to the electromagnetism. The field, which is the addition of the electric potential and the electric field and the magnetic field, okay, is a vector. Okay. Two differential forms, let us talk in the right way. Is a differential form is obtained from the vector potential, which is differential one form, but minus sign here. Okay, as not only as an external differentiation, which is this, but as a general differentiation. External differentiation only yields some of the equations of Maxwell's equations, but all the Maxwell equations are written with Clifford differentiation, Keller differentiation. This is the general Clifford differentiation. This accounts for all the equations relating fields with potentials. And a new differentiation, a new Keller differentiation yields current because the external differentiation of an external differential only yields zero, but not the currents. Okay? So we need the scalar differentiation, the Keller differentiation, to get the currents. The currents are three differential. Okay? And finally, but this is not my topic to explain. Only to introduce and to advance. In quantum mechanics, we have a problem. The problem is that we want, there is the relation, the round relation between energy and the capacity. We know this. But the problem is not, the historical problem was to find the root of the Klein-Fock equation. It is the equivalent of the classical equation, the relativistic equation for momentum and energy. This is the Klein-Fock equation. This is the mass of a particle, and maybe the electron, for instance, and Redinger searched for the root of this equation. But for a solution, or for a model of the equation and a solution for the wave function, but of scalar type. And this was his error. He then lost the prestige of finding the solution to the lattice solution. And who found this was Dracula with many complex matrices. This is simple. This is only written in scalar calculus. The rule of the equation must be of this kind. Symbolically, we have coordinates. Okay? We have coordinates. But there is a problem, and now finish. The problem is that we have here, for instance, grade 1, for instance. Differentiation gives grade 2 for the stereo differentiation and grade 0 for the scalar differentiation. But then, if I have here grade 1 and here grade 0 or grade 2, cannot be the same, the wave function. This means that we cannot have solutions, wave functions of homogeneous grade. We need elements of heterogeneous grade to satisfy this equation. This is the important point. And this is just related with idempotence. But idempotence are the topic of user, no? Los vinos. Who explains? José?
No, well, it depends. El coche escoba, whatever he doesn't do,
Okay. So I finish here.
And from there, he got solutions, okay, spinorial solutions. And it is a beauty based on idempotence, okay? And he cracked the machine and he obtained, okay, electrons and positons with both chiralities. Okay, that's the beauty of color. And his quantum mechanics, he's not going to assume all the philosophy which came, okay, from the non-relativistic quantum mechanics. He wrote an equation and then he cranked the machine. So he got the physics from the mathematics.
He found the relation between electrons and positons, the addition of power density currents, without the second quantization. This is the usual way explained in physics to do electrons and positons.
And the equation of
the second one.
Yeah, the continuity equation that he is going to find from first principle, so to speak, from his equation, is not just the usual continuity equation. Partial of rho in respect to t, okay, plus equality of divergence of j equals 0. No, he's going to get partial of rho 1 with respect to t, plus divergence of one current, plus partial of another rho with respect to t, plus the divergence of another current equals 0. The conserved thing involves something which has one of the rows is always non-negative, the other one is always non-positive. So these does not apply to probability. So the having interpretation has to do with the Dirac theory. If you can get the same results for the hydrogen atom and so on, using the Keller equation, so both theories are at par in that regard. In that specific regard, in other regards, the Keller equation is much better. But in addition, now the Keller equation is not compatible with the Copenhagen interpretation. The Copenhagen the probabilistic, the interpretation of the wave function as a probability amplitude, okay, that is an emergent concept in a specific situation. So the Keller quantum mechanics is infinitely better than the Dirac theory. The Dirac theory was great for its time, okay? But one can do much better, and I don't know where theoreticians are looking at it. And that is only with the scalar value differential forms. Imagine if you had tensor value differential forms, I don't find they are but three value differential form. Then you can take the theory of particles. I mean, U1 is U2 is U3, but going not through group theory, but through algebra.
Okay. So this is the expression. The expression of the continuity equation of Keller is this possible? And right?
What? Now it is history. Now we talk about whatever you want. Supposedly, you should talk about exterior and interior differentiations and the Leibniz rules of Keller.